Welcome back to a new video about system identification. This is our example number 5, and we continue with another example of a second order system. Again, we will look at our calculation step by step, and we will verify this using MATLAB simulations. So let's look at an example. What we have is then the following. Given the step response of a system, this plot, and the unit the input for that system R is a step with an amplitude of 4, which is shown here in red. So we have this input in red, which has an amplitude of 4. The response is given in black, which is the output. So I want to use this plot, given information, to determine the transfer function of this system. So what do? Let's look at our solutions. So observations from the graph, and specifically now, of course, the output, we can see that the shape of the curve has a shape which is a higher order system, higher than first order. So it can be second order, it can be a third order, maybe a fourth order system. But I will just assume as a simple step that this is a second order system. I can also see that from the starting of the starting slope of this at the origin, it has a slope of 0, and it has a shape of an overshoot, and it will settle down to a value. And I just assume it is a second order system, not a third order system. So let's use this in our analysis. So this is a second order system. The steady state value of this system, so y at infinity, is 8. You can see that here. It's already given. I can also see that the settling time, which is then given by TS at 2% criterion, is 5.8 seconds. You might ask, how can I determine that? If I look at the plot, this 8 is our steady state value, and settling time with a 2% criterion is determined by having a region, error region between this 8 value of 8. So you can go up by 2% and go down by 2%. And when this curve response reaches that region and it stays in that region, that's actually the settling time of your system. So if my response goes in that region of 2% up and 2% down and stays in that region, the first moment, that is the settling time I will then have for my response. So in this case, I have just determined what the 2% down of this one, also 2% up. I have seen from this plot that if I go 2% down, that will be 7.84, and that is the first time I am in this error region, and I will also stay in that region. So that will be then our 5.8. That will happen at 5.8 seconds. I can also see the peak time is 3 seconds, and also the value of the peak is 9, and we can now use these data to determine the transfer function. And again, we assume, of course, it's an all-pole second order system without any zeros or any delay. So again, this is the transfer function for the second order system. We have the KDC, which is the steady state gain, DC gain. The other one is the omega, which is the natural radiant frequency, and the damping ratio, which is then zeta. So we need to determine these 3 parameters for our transfer function. So let's then look at our transfer function specifically in this case. So first, the DC gain. The DC gain, or the KDC, is equal to the DC value of your output, or the steady state value of your output, divided by the steady state value of your input. In this case, the value of your output, the steady state value, is 8. But the steady state value of your input is, in this case, the amplitude is 4. So it is not a unit step input as we did in the previous example 4. So that's then 8 over 4, which is then 2. So it has a KDC of 2. That's first. So I have already one of these 3 parameters. So looking at the overshoot from the graph, what I see is the peak value minus the steady state value over that steady state value. That's actually the ratio you can then use to determine the MP as a scalar, which is then the overshoot. So MP is overshoot. So it is 9 minus 8. So it is 9 minus 8 divided by 8. So it's actually this difference between the steady state value and the maximum value, that difference over the steady state value, which is then 1 over 8, which is then 0.125. So it is 12.5%. So using this and also the formula for the zeta, we have seen this of course also in the root locus design method for the controllers in the other videos, then you can calculate your zeta, which is then 0.552, very close to that value. So I have also determined the zeta, which is then this unknown. So I have now only omega n left, which is then the natural radiant frequency. But in this time I have of course the settling time and not the peak time used for my calculation. I will do that purposely so that you can see that this is also possible using the settling time instead of the peak time. You can also do that for yourself by using the peak time, and you can then determine the transfer function as we did in the previous video. In example number 4, we have done this for another second order system, but I will do that in a different form such that you can see that this is also another way to determine the transfer function of a second order system. So the settling time with a 2% criterion is 5.8 seconds. So it is 5.8. The formula for the settling time can be rewritten in this form, so I can then determine the absolute damping, which is then the sigma of d, which is then 4 over that settling time. Then I have 4 over that 5.8. Now I will then get, if you do the math here, you will get 0.69 for my absolute damping. Absolute damping, sigma of d, is equal to the zeta times the omega n, which is just the product of these two. That is the absolute damping. Now I know already the zeta. I know also the sigma of d, so I can calculate what the omega n is by using omega n is equal to sigma of d divided by the zeta. So I will do that and I will have very close to 1.25 radians per second. That is the natural radiant frequency for this system. So I have now all the necessary parameters. I have the KDC, the zeta, and also the omega n. So then we have the following: collecting the terms, substituted in this transfer function model. I have this one, and if I now simplify this, I have then this expression, which is then 3.12 over s squared plus 1.38 s plus 1.56. So that is our transfer function, and we will need to verify this in MATLAB simulations. So let's look at our next step. So transient response, and we start with the first one, and that is then the step response. This is what we have from our step response. That h, I have now changed that to h4. Why? Because I had a response which is due to that input of a step, and that has an amplitude of 4. So I have just made this h4 to emphasize that it has an amplitude of 4. So I can see the values from this transfer function. You can see this is 8. So if I just substitute in here the value of s is equal to 0 and 0 here, and I will do this 3.12 over 1.56, I get a 2 here, times the 4, of course. Due to that input I have then the 8, which is then the final value. So that's correct. I can see the values in here also. The peak value was 9, and overshoot is here 12.5, so it is 0.125, which is very correct, and that occurs at 3 seconds. It was a peak time, so this is also the confirmation of our peak time. What I do see here is a little bit different than what I have used for my settling time. The settling time here is, according to the simulation, is 4.7 approximately for my settling time, which is much smaller than the 5.8 seconds I have actually determined for my plot. So how is it possible? Now, the one way to analyze this or reason this is the following. The settling time formula we have used for 4 over that settling time, or settling time with the 2% criterion is 4 over that absolute damping ratio, is an approximation actually. So it is actually, the formula has some region which is not exactly 4 over that absolute damping ratio, but absolute damping, it is a little bit in between the 3.9 and 4.7 for that 2% criterion. So most of the time, most books use 4%, but it is, of course, can be a little bit smaller. It can be also a little bit larger than what you have estimated or calculated. So that is not really a surprise for me, that this is a little bit lower. So, and I also see that this time, so you can confirm that, at time 5.88, that's actually what I have here. I have, or 5.9 actually, but I had 5.8 of course in my plot. It is 7.88 and I had very close to what we'll see here. So that is also a confirmation actually that the plot is correct, but the settling time is smaller than what we have used from the plot. That is of course possible because we make an estimation from the given plot, so you might have some errors, but of course in the total sense we can see that the overshoot is correct, the peak value is correct, the peak time is correct, and also the final value is correct. So that's actually a very nice result from this unit step response, the step response. And these are the values again. Steady state value is 8, settling time is 4.67 seconds. This is then of course smaller, approximately 1 second smaller than the 4.8 seconds. The peak time is correct, the value of the maximum value is also correct, and the overshoot is also exactly as we have calculated. So that's all fine, and we assume or accept that this transfer function is correct. So if I now look at the Bode plot, this is the Bode plot, I can see the following, again, from this transfer function. In this case, since we are looking at the system itself, we only look at the age, not 4 times age. So we only have the age itself. Then at DC approximately, I can see it is again 6.02 dBs. That's from this DC gain, and you can of course calculate it using this, because the DC value from this age is, of course, if you just substitute for the s is equal to 0, you will get 2 here. Substitute that in this formula, you will have 6.02 dB. So that's correct. If I now look at this label, again, I see a peak gain of 6.74 and at that frequency of 0.781. And we will verify this. This is the associated phase with that one, and this is the bandwidth again. So you go down by 3.01, and it will be at 3.01. So if you go down from this magnitude to that magnitude, that will happen at 1.51 radians per second. And this is the bandwidth of our system. So we will verify this. Again, associated phase for that bandwidth is shown here. So again, the KDC, the value of R, the damping ratio, and we have also the omega n, which is the natural radiant frequency. So what do I have? I have then, of course, the peak gain. This is given, of course, in dBs. First, I calculate the scalar value of that one. This is this formula, KDC over that 2 zeta times the square root of 1 minus the zeta squared. Substituting the values, I have then 2.17 approximately. If I go to the dBs, it will be 6.74 dBs. That's exactly as we have in the simulation. The resonant frequency, it's actually this one, so the resonant frequency omega r is omega n times the square root of 1 minus 2 times the zeta squared. Substituting the values, I have then 0.781 radians per second, which is then exactly as we have here given in green. So the final one, which is then the bandwidth of our response, which is given by this formula. If I substitute the values again for omega and also for the zetas, all of them in this expression, I have 1.51 radians per second, which is then exactly as we have simulated. So you can see it is all confirmed by this Bode diagram. We have the bandwidth, we have the peak value, we have also the resonant frequency. All of them are correct according to the Bode plot. So that is actually what we have. So that's all fine. And again, as a second verification in the Bode plot, we can see that this transfer function is correct, and which will then model the response and also the system itself for this example. So let's look at also in the real-time plot in MATLAB and see that in more action. So next step is MATLAB. So we are now in MATLAB, again, I prepared a script for this example number 5, system identification. Again, defined the Laplace parameter, and from the plot we have determined these: the settling time, the peak time, the maximum value, the steady state value of our output, and also in this case our amplitude for the input signal, which is then just input step. So it is 4. Now the parameters of the system, I have again prepared the parameters KDC, MP again, zeta, and in this case sigma d, because I don't use the peak time. I use the sigma d, which is the absolute damping or real part of the pole. That's then 4 over that settling time, and then I can calculate the omega n by using the sigma d divided by zeta, which is then discussed in the calculations part. Now this is the model I have then used to determine the transfer function of the system. And the body plot parameters can be then calculated using these formulas. I have then used this also in a discussion of the body plot. So this is the resonant frequency, the peak value. This is the peak value in dBs, or peak gain. This is the resonant frequency, and this is the bandwidth of our system. So let's run this and check what's going on. So run this, and I will check just, of course, the H. And let's see what it is. It's 3.1 approximately, 3.12 over S squared plus 1.38 S approximately, and 1.56. So this is actually very close to what I had. We had 3.1 here, and we had 1.6 or 1.655 approximately here. So it's very close to what we have here, also from the calculations. Now we can then do the verification for the MR, so the peak value, which is then 2.17, and I can also do that MR and dBs. You can see it was then 6.74. Now you can of course check the other one, but let's jump directly to step response and see what's going on. So the grid on, of course I need to do the step response with the amplitude of 4, so there's actually 4. So you can do that by defining a new transfer function, or you do this just 4 times h. Then you get the following. Of course I need to make a semicolon here, so I will then have the response. That's the response I have here. Let me make it larger. So this is the unit step, the step response with an amplitude of 4. So let me get this. So let me check the characteristics, the peak value. You can see it's 12.5, so let me make it larger. 12.5, and I replace it here, so whether here, so 12.5%, so 0.125. The peak value is 9, at that peak time of 3 seconds, so it's all fine. Let's also check the steady state value, which is 8, so all fine, all correct. Okay, and the settling time, because it was in our case 5.8, but in this case it is 4.8 approximately, 4.7 actually, so that's much smaller. Also make this a little bit larger. Also this a little bit larger. And of course we can look at the 5.8 exactly, so what's actually going on there. So if I go there at 5.8, I can see it is 7.88, and we had actually here 7.84, so it's also very close to what we have from our plot. So this is again a confirmation of our transfer function of our system. So that's what we have from the plot of the unit of the step response. So let's also look at the body plot. So body, again body, and then H, and then grid on, and then we will see what's the body plot doing. Again, make it larger. Let's look at the peak and also the the DC gain. So this is the peak. You can see that DC is 6.02 dBs, so actually what we have discussed. You can also check the bandwidth. So approximately 3 dBs down, so it's 1.51 radians per second, exactly what we have calculated. And I've also see here the peak value and also the peak frequency, which is then of course resonant frequency. Let me also make this larger so you can see that easily. And this is also what we have. So this is actually the DC value, approximate DC, very low frequencies. You can see the peak value, exact same as we have calculated. Again, in real time, you can see what's going on in the body diagram for my bandwidth also. So all confirmed, and again, in real time, you've seen that the system is also verified using this body plot and also the step response we have seen in MATLAB. So this was an example about another second order system in this example number 5. We will continue with different topics and different examples. So if you have questions, comments, or any issues you don't really get, please let me know. I will try to answer them as soon as possible. Thanks again and see you next time. And don't forget to like and share and take care.